everyone. We are Group 11. I am Suraya Akhtar and I am here with my teammates Madhir and Daniel. Today we are presenting our linear algebra project on the application of linear system. Usually we see matrices as just a number, but today we want to show you how engineers actually use this system to solve real world problems and build better technology. Our objective today are to explore how linear systems apply to electrical, civil and mechanical engineering as well as data science. We will focus on applying the AX equal B model to solve a regression problem and using Kirchhoff laws to solve DC circuit. We will also touch on structural stability and network flow analysis. So, what is linear system? It is a set of linear equations sharing the same variables. The general form is ax a1 x1 plus a2 x2 plus dot 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 an xn equal b. In engineering, we convert this into the matrix from ax equal b. This provides the essential framework for solving everything from circuit analysis to structural design. Look at a specific application in electrical engineering. Our goal is to find three unknown currents I1, I2, I3 in a DC circuit. Our components include a 10-volt voltage source and three resistors R1 at 2 ohm, R2 at 3 ohm and R3 at 4 ohm. To solve this, we use Kirchhoff's law. First, the current law at the node gives us our first equation I1 I minus I2 minus I3 equals 0. Next, the voltage law for loop 1 gives 2I1 plus 3I2 equals 10 and loop 2 gives us 3I2 minus 4I3 equals 0. Now we have three equations for three unknowns. We then convert this into matrix from AI equal V. The A matrix contains the resistance and nodes relationships. I is our target current vector and V is the voltage source. So this presentation is what allows us to solve the system using computational method. We can solve this using matrix inversion or Gaussian elimination by performing raw operation on the augmented matrix to reach an upper triangular form, and using back substitution we found our final current value I1 equal 2.692 ampere, I2 equal 1.538 ampere and I3 equal 1.154 ampere. In engineering, validation is K. Our KCL check proves 1.538 plus 1.154 equals to 2.692. More importantly, the power supplied is 26.92 watt, exactly matches the power dissipated by the resistor. This mathematical consistency confirms that our engineering model is correct. To visually validate this circuit result, I use the first circuit simulator. This image shows the exact current parts for I1, I2 and I3. It shows how the 10-volt energy is distributed across the network exactly as we calculated. To conclude, these systems are vital for large-scale engineering. Nodal analysis is used for city-wide power grid analysis, IC design for microchips with millions of transistors, and control systems to establish robotics.
Now let's scale up from microchips to massive infrastructure. In civil engineering, our primary imperative is structural integrity. Whether designing a bridge or a tower, we employ a technique called nodal analysis. The government principle here is static equilibrium. For a structure to stand still, the net force to at every single joint or node must sum to zero. Even a simple truss generates a massive system of linear equations that must be solved simultaneously. Let's look at concrete case study. Here we have a triangular truss supporting a vertical load of 10 kilonewtons. We need to determine the internal force in beams F1, AB, and F2, AC to ensure they won't snap. By resolving the force vectors of node A using trigonometry, specifically the sines and cosines of the 60-degree angle, we derive a linear system directly from Newton's law. Instead of solving this algebraically, which is slow, we translate it into a matrix. We encapsulate the system into the matrix equation ax equal to b. Matrix A represents the geometry, the angles. Vector B represents the external load, 10 kilonewtons, and vector X contains our unknown forces, AB, AC. By calculating the inverse of matrix A and multiplying it by the load vector 6, we arrive at our result, minus 5.75 kilonewtons. Please note the negative sign. In engineering, this is critical. It indicates that the beams are under compression. They are being squeezed, not stretched. Why does this calculation matter? Knowing that the members are in compression allows us to predict buckling. Steel behaves differently when squeezed and pulled. Compression members must be thicker to prevent building, and tension members can be thinner cables. Linear allows us to optimize materials and ensure safety before construction even begins. Transitioning to mechanical engineering, we encounter dynamic systems such as vehicle suspensions. These are what we call coupled oscillations. Because the components are mechanically linked by springs, movement in one part propagates through the entire system. We cannot calculate the wheels in isolation. We must solve for the system as unified whole using Hooke's law. Consider this two-mass system. We have two masses connected by springs with stiffness values of 10 and 20. We apply a force of 5 newtons to the bottom mass. Note that mass 1 is connected to mass 2. This creates a dependency. The equation for mass 1 must count the spring pulling it up and the spring pulls down towards mass 2. This dependency creates a complex system of linear equations. We aggregate these interactions into the stiffness matrix K20. I 10 and 20. I want to draw your attention to the matrix values. 30 represents a total stiffness holding mass 1, K1 plus K2. The minus 20 represents a physical coupling between the masses. Solving the equation Kx equal to F using the determinant and inverse method gives us a precise displacement. Mass 1 moves only zero point 0.5 meters mass 2 moves 0.75 meters. This calculation is a fundamental tool for vibration control. By analyzing and adjusting the values in the stiffness matrix, automotive engineers can tune a car suspension. They can mathematically adjust the ride to be sporty or comfortable without building physical prototypes. Linear algebra converts physical vibration into controllable data. Thank you.
Today I will talk about the application of linear systems in data science. In data science, we often work with real-world data that involves many variables at the same time. Linear algebra, especially linear systems, provides a mathematical foundation to model these relationships and make sense of complex data sets. This allows data scientists to analyze data efficiently and build predictive models. At the core of data science, many problems involve finding a relationship between multiple variables, also known as features. These relationships can represent a system of linear equations. Using matrix representation, large data sets can be stored and proceeded efficiently. This structure allows mathematical methods to be applied systematically, which is essential when working with real-world data at scale. One of the most fundamental applications of the linear systems in data science is linear regression. Linear regression can be written as a system of linear equations, for example, in the form of ax equal b or y equal x beta. Here the matrix represents the data features, the unknown vector represents the model parameters at the output, and the output represents the predicted values. By solving this linear system, data scientists find the best fitting line or hyperplane that minimizes prediction error. This method is widely used in tasks such as sales forecasting, price estimation, and trend analysis. Many machine learning models rely on linear systems during training. In supervised learning, optimization problems can often involve repeatedly solving or approximating large systems of linear equations to adjust the model parameters. Even the models become more complex, linear approximations are commonly used to reduce computational costs and improve performance on large-scale datasets. Data science applications datasets are often high-dimensional, meaning they can contain a large number of features. Linear systems help analyze dependencies between these features and identify redundant information. By understanding these relationships, data scientists can simplify models, improve efficiency, and make results more unpredictable. The difficulty of applying linear systems in data science does not come from solving equations manually. Instead, it comes from scaling mathematical models from real-world data. Real datasets are often noisy and incomplete, and the number of variables can be very large, resulting in high-dimensional linear systems. Another challenge is computational constraints. As datasets grow, solving linear systems efficiently becomes critical. Data scientists must balance accuracy, speed, and available computational resources when working with large-scale machine learning. Overall, these examples show that linear systems are not just theoretical concepts, they form a foundation of modern data science, and by connecting mathematical theory with real-world data analysis and machine learning applications. To conclude, this presentation has shown that linear systems are powerful and universal tool across science and engineering. We began by introducing linear systems and their matrix form, which provide a structured way to model complex problems with multiple variables. In electrical engineering, we saw how linear systems are used to analyze circuits and determine unknown currents using Kirchhoff's law and metric methods. In civil and mechanical engineering, linear systems help engineering to analyze structural stability, force distribution, and coupled systems such as vibrations, suspension models, ensuring safety and performance before construction and implementation. Data science perspective, linear systems form the foundation of models such as linear regression and machine learning optimization. They allow us to work with high-dimensional, noisy, and large-scale datasets, turning raw data into meaningful predictions and insights. Overall, linear systems connect mathematical theory with real-world applications, making them an essential foundation for modern engineering and data-driven technologies. Thank you for your attention in Group 11, Linear Algebra. The theme is Application to Linear Systems.